I'm Catherine Conlon, and this is my Physics Lab 2 projectile motion. The purpose of this lab was to demonstrate the expected trajectory of a ball of paper being thrown due to gravity, and then using graphing models to compare our experimental tests to the expected, assuming it obeys Newton's laws of motion, with a net force of just gravity for one of our models, while we had a net force of gravity and drag for our other computational model. For a result summary, the results showed us that the forces acting on the system were both gravity and drag, because when drag was not accounted for, our results were way off, and it formed a perfect projectile, which is only in a perfect system where only gravity is at hand. This is due to the fact that Newton's second law is force equals mass times acceleration, and if the only force acting on the system is gravity, we can predict its path. We can also predict objects' paths by knowing all the forces acting on the object, such as drag, because this tells us what the acceleration is if we also know mass. We used both computational and observed models to explain Newton's second law and how it applies to projectile motion, acting in two directions, x and y. The system for our experiment was the ball of paper, and the surroundings was everything else around it. Here are some screenshots of our experimental model in action, where we threw the ball of paper and it went in the trajectory. Here are the predicted models we created by doing computations through GlowScript coding. We have the one with drag and the one without drag, and as you can see, the one with drag looks much closer to the correct trajectory. Here's a comparison of x versus y trajectories for all three models: the one with drag, the one without drag, and the observed model. As you can see, the one with drag is much closer to the path of the observed than the one that we created without drag. The observed in the part of the experiment was where the paper ball was thrown into the air across a desk, and we used a tracker to determine the position of our ball for each timestamp, setting the origin as right below the ball's initial starting position. As you can see, I included a screenshot of the tracker of our experiment and how it was working. We created the origin right below the ball, and we tapped for each timestamp to get our trajectory. In the predicted, however, we use coding to analyze the same object's motion based upon obeying Newton's second law of motion, force equals mass times acceleration. If we can predict the net force acting upon the object, the velocity should be able to be predicted the entire time and its change in position. We can then predict the object's trajectory/path of its motion. In this case, the forces were acting in only the y direction for a model that just depended upon gravity, which is why we saw a constant slope for the x position versus time without drag. Using the initial conditions of our observed model, we built the predicted model. As you can see, we had initial conditions for the position of the ball and the velocity of the ball, and we obtained these through looking at our observed model's data. We made multiple assumptions for this experiment. For the first computational model, we assumed only gravity was acting on the object. For the second one, we assumed only gravity and drag were acting upon the model. We had a major source of error between the observed and predicted, and here's why. One cause for error is that in the observed model, while throwing the ball, we didn't release it immediately, meaning our hands were acting as a force upon the ball for longer than the initial. As you can see, I've included a photo when the ball finally left our hands, and you can see that we lifted it quite far. This affects the initial position where just drag and gravity are acting upon the paper ball, and the net force for part of its path. This is a reason for our computational model was slightly off for its path, although the one with drag was still much closer. When we were coding in GlowScript, we created a model for the projected trajectory of our thrown paper ball using both the velocity update and the position update formulas in a loop that was able to find the motion of the ball along small time steps to create a graph. Most importantly, we also calculated our net force acting on the ball, and this included whether we included drag or not. As you can see, I've included code of how we calculated the force gravity and the force drag, and I've included the code for the ball, for the position update formula and the velocity update formula, and the formulas they would derive from. I've also included the timestamp and how we calculated that and updated it. Finally, what if the object was thrown straight up? How would this affect the time it took to reach the ground if thrown with the same initial velocity? To explain this, I've included a photo of a projectile motion velocity vector next to a straight up velocity vector. As you can see, for the projectile motion, it's at a slant, and the velocity is split into two components, x and y, while the straight up velocity vector is going completely in the y direction and does not have to be split into components. This means that the object thrown straight up with the same velocity would reach the ground last. The arrow thrown straight up does not break its velocity into components, so it is able to reach a greater height before falling back down than the object has to follow a parabolic path, with the velocity being weakened by being split into components. This means it would take the object thrown straight up longer to reach the ground, since it goes a greater height and gravity has more to overcome before it falls down, assuming gravity and drag are the only forces acting on the object in this event as well. Finally, what does it mean? Do any models predict a terminal velocity? If not, what similar experiment could we use to design to find our project's terminal velocity? No, none of the models predict a terminal velocity because terminal velocity is achieved when both the drag and gravity are balanced, giving the object a constant velocity which we did not observe. If any of our models had reached terminal velocity, the acceleration would have stopped. We could design a similar experiment to find the terminal velocity by throwing an object higher so it has longer to fall and air resistance to build up to reach its terminal velocity. Thank you.